right, the focus for today, holes and asymptotes. So we're going to be doing some graphing. And these holes and asymptotes, they're really mostly coming up in rational functions, so that's going to be our focus today. To start, what I'd like you to do is first determine the domain for each of these rational functions. So please go ahead and do so. Pause the video, give it a try. All right, so remember to find the domain of rational functions. You look for whenever the denominator is not equal to 0. So what we do is we set the denominator not equal to 0 and solve for x. So add 4 to both sides, and we get x is not equal to 4. So this would mean any x values work except for when x is equal to 4. Same idea here. You set the denominator equal to 0. We get negative 4x cannot equal 16. Divided by negative 4, we get x equals negative 4. Or in other words, x cannot be negative 4. Okay. When you have a quadratic, or rather anything larger than just a singular x, what we want to do is we want to factor that out. So look for numbers that multiply to negative 3 and add to negative 2, which is, in this case, negative 3 and 1. And then we can set both not equal to 0, which is a little weird to say, and solve for x, where we get x cannot be 3 or negative 1. Lastly, again, over here, we can factor out a GCF on the bottom, so we get x times x minus 3. So x cannot be 0, and x minus 3 cannot be 0, so x cannot be 3. Alrighty. Okay, so domain. Whenever you have things like this where x cannot be certain values, what happens is you have either holes or asymptotes in those cases. So what we're going to do here is look at how both of those cases apply. So to start, you'll always want to look for holes first and then for asymptotes. So we can find holes by looking for variables or factors with variables that cancel from the top and bottom. We find vertical asymptotes by setting the denominator equal to 0 after canceling. So you've canceled to find holes first, and then you can do your vertical asymptotes. So as we look here, this first problem, we look to top and bottom, see is there anything I can cancel, any factors I can cancel? Well, this rational function is set up with just an x on top and an x minus 3 on bottom. So it's already in its most factored form, and these are not the same thing, so you can't cancel. You cannot just take away x's from the top and bottom. Math doesn't work like that. Remember, you can only cancel entire factors. So in this case, there aren't any holes. So what you do to find your vertical asymptotes, just like with finding domain, you set the denominator equal to 0. So we get x equals 3. So what that means is there would be a vertical asymptote at x equals 3. So that would be our line right here. There will be a horizontal asymptote here as well, which is something we will get to, but for now I'm just going to ask you to trust me. There's a horizontal asymptote at y equals 1. Trust me, we will get there today, but we're just going to start with vertical asymptotes and holes to begin. So we know rational functions, essentially, they look kind of like this. That's not always going to be the orientation. They're not always going to be in the first and third quadrant. So what we can do then, essentially, to figure out what this looks like, just plot a couple points, get the general picture. So like if I plug in 4 for x here, I'll have 4 over 4 minus 3, or 4 over 1, which is just 4. So I have a point at 4, 4. So I've got a point up here, so I know it's going to be in this quadrant. Over here, just pick another one. So like, let's say 0. I plug in 0. 0 over negative 3 is 0. You can plug in some more points if you want to. Like if I want to plug in, let's say 2. 2 over -1 is -2. But with rational functions, your function always trends along these asymptotes. So as long as you have a point on either side of the vertical asymptote, you can usually get a pretty good idea of the picture. The reason we need to plot points on both sides is just to make sure they're in the proper quadrants. Like if I plot 2 and I got a point up here, I would know I would need to graph it up there. Okay. For the second problem, this is one where we will have a hole. It's kind of told you there. But remember, to look for holes, you look for variables or factors that can cancel from top to bottom. So as we're looking here, in this case, we have an x minus 3 and an x minus 3 on top and bottom. So to determine where the hole is, you set your canceled piece equal to 0. So in this case, x minus 3 equals 0. We have x equals 3. So what that means is there is a hole at x equals 3. So what we do here, so we find holes by looking for factors with variables that cancel from top to bottom. Then what we do is we set the canceled piece equal to 0. So now what we have after canceling is we have f of x equals x. So that's a linear function. So it has y-intercept of 0, slope of 1, so we go up 1 over 1. But we have a hole at 3. So the way we determine where that hole is you plug in 3 for x here. So when we plug in 3 for x, we get 3 for f of x or y. So that means there's a hole at 3, 3. And I made my hole really big, but just to kind of make sure we understand. So just to recap, you find holes by looking for things that cancel top to bottom and then set that canceled part equal to 0. After you've done that, then you set the denominator equal to 0 if there is one anymore. And that's how you find vertical asymptotes. Okay. So we're going to put those processes, those skills together here. So to begin, we first look top to bottom. Is there anything we can cancel here? In this case, the answer is no. There's nothing you can cancel, so there won't be any holes. So I'm just going to put none. For your vertical asymptotes, you set the denominator equal to 0. So first thing I can see here is we can factor 3 out. So we get 3 times x squared plus x minus 6 equals 0. Now let's look to see if we can factor this into things that multiply to c and add to b. Multiply to -6 and add to 1. That would be positive 3 and -2. So now we have our factors, x plus 3 and x minus 2. So to find our vertical asymptotes, in this case, which is interesting, we set x plus 3 equal to 0, which will give us x equals -3. So that's our first one. And we set x minus 2 equal to 0, which will give us x equals 2. So x equals 2 is our second. So we have an asymptote here at -3. We have an asymptote here at 2. Okay. And in this case, believe it or not, again, you just kind of have to trust me. There is no vertical asymptote. Excuse me, what I meant to say was there is no horizontal asymptote here. And again, we will get there. We will talk about them, just not yet. So in this case, this one is pretty hard to graph. What you could do, I mean, as always, is you can plug it into your calculator to give you kind of a general picture of what that looks like. The main goal is being able to find these asymptotes, not as much graphing. But what we will have here, and what you could do is you could still just plug in points. So like if we plug in, like let's say 0, we get 1 over negative 18, so really close to 0. If we plug in, say, 1, we get 1 over 3 plus 3, which is 6, minus 18 is negative 12, so 1 over negative 12. So a little closer to 0. If we plug in, I don't know, we can't get to 2 because it's an asymptote. But if we plug in 1.5, we're going to get something that ends up going a little more positive, going up here. Whereas when we're working over here, I believe we should get something that goes in this direction. Okay. All right. Okay, let's check another. So in this case, we want to first look to see if things cancel. There's a lot going on. So I think the best way to determine if things cancel, because you do cancel variables or factors, is to start by factoring. So we have x squared plus x minus 6. This will factor into x plus 3x minus 2. Down below, I'm noticing we can at least start by factoring out negative 4. So we'd have negative 4 times x squared plus 4x plus 3. And then we can factor out that x squared plus 4x minus 3 into x plus 3, x plus 1. Okay. And I'm looking and I'm seeing two things will cancel. So we have this x plus 3 that'll cancel. So what that means, so we have x plus 3, we set that equal to 0, solve for x, we get x equals negative 3, so we'll have a hole when x is negative 3. Now with what remains, now you can solve for those asymptotes. So you set the denominator equal to 0, which in this case is negative 4 times x plus 1. Set each factor equal to 0, which negative 4 has no variable, so your factor is really just x equals 1, so we get x equals negative 1 as our asymptote. So we have an asymptote at x equals negative 1. Again, you're just going to have to trust me a little bit in terms of horizontal asymptotes. There is a horizontal asymptote. It's at negative 1/4, so really close to 0. We have a hole when x is negative 3. So the way we determine our hole, as well as the way that we graph, is by you look at your already canceled function. So looking at our canceled function, which in this case is f of x equals x minus 2 over negative 4 times x plus 1. So you look at that canceled function and you plug in values. So as we think about like our hole here, if we plug in negative 3 here, so f of negative 3 is going to be negative 3 minus 2 over negative 4 times negative 3 plus 1. So negative 5 up top over negative 4 times negative 2, negative 5 over 8. So when we plug in negative 3 for x, we get negative 5/8, which is below the asymptote. And since we do have that hole there, it does tell us that our function is going to extend in these directions. Because with these two asymptotes, with a vertical and horizontal, it is always going to be on one side. It's not going to be on both, because then it wouldn't be a function. It wouldn't pass the vertical line test. But on the right side, it could also be over here. That is possible. It's usually in the opposite quadrant, but it is good to check. So 0 is a nice and easy check. If we plug in 0 here, we're going to get 0 minus 2, which is negative 2. Negative 4 times 1, or negative 4, so we get 1/2 when you plug in 0. So it is above the x-axis, above our asymptote, so it's going to go something like that. So you can see when I'm graphing, I'm not expecting a lot, just basically that you can put them in the right quadrant. Okay. All right, you have 2 more here. I'm going to ask that you give the video a quick pause. Try these both on your own. Determine the vertical asymptote, determine the hole. Give it a pause, try it. Okay, we are back. So start by factoring if you can. So let's pull a 2 out of the top. Down below, numbers that multiply to 2 and add to 3 would be 2 and 1. Up top, we can continue to factor. Multiply to 6 and add to 5. Well, that's 3 and 2. So I'm looking, we've got x plus 2 will cancel. So that means for our whole, it's going to be whatever makes that x plus 2 equal 0, which in this case would be negative 2. For our vertical asymptote, we rewrite our function post-cancellation. So we'll have 2 times x plus 3 over x plus 1. And then we set the denominator equal to 0, which in this case would be x plus 1. So we get a vertical asymptote at negative 1. So at negative 1, we have a vertical asymptote. In this case, you're going to have a horizontal asymptote at 2. Again, just trust me, we'll get there. And we'll have a hole at negative 2. So let's plug in negative 2 into our canceled function. We're going to get 2 times negative 2 plus 3 over negative 2 plus 1. So 2 times 1, that'll just be 2. Negative 2 plus 1 is negative 1, so we get negative 2. So negative 2, negative 2. Like so. From there, plug in another. On the other side, so let's try 0. 6 over 1 is 6, so you get a point up there. So you just pick a point on either side of the vertical asymptote to give you just a general idea of what it looks like. For the next, so starting, I see we can factor an x out of the top. Down below, we can factor 3 out. And now let's see if we can factor any further. Oops, that would be 2. And that would be 3. Up top, this will factor into x minus 3x plus 3. Down below, it'll factor into x minus 3x plus 1. So x minus 3 cancels. So that means we'll have a hole at x equals 2. Next, we set the denominator equal to 0. So x plus 1 equals to 0 means we have a vertical asymptote at negative 1. In this case, there is no horizontal asymptote. And what we can do next is you're just going to have to do a little bit of graphing here. So at the very least, we want to find our hole. So let's write out our canceled function. It'll be x times x plus 3 over 3 times x plus 1. So plug in 3 for x. So 3 times 6 is 18. 3 times 4 is 12. Yep. So we get 3 over 2, or 1.5. So when we plug in 3, we get 1.5. So that's where we'll have our hole. As you continue to graph, you can just use your calculator here to get kind of a general picture. But essentially what it's going to look like is something along these lines. We're not really going to get into this here, but what it has actually is it has a slant asymptote. So it does approach something, but it approaches something with a slope, which is a little interesting. All right, so that covers our vertical asymptotes and holes. Next, we just need to dig into our horizontal asymptotes. So for horizontal asymptotes, there are 3 options. There's bottom heavy, top heavy, and even Steven. Those are our 3 options for horizontal asymptotes. So with bottom heavy asymptote, so we're referring to the highest exponent. So this is bottom heavy because we have a bottom of 5 and a top of 2. So bottom heavy, that 5 being larger than 2. When it's bottom heavy, you have a horizontal asymptote that is always at y equals 0. And I won't make you graph the rest. When it is top heavy, so when the exponents on the top are larger than the exponent on the bottom, the degree is higher on the top, we always have no horizontal asymptote. When it is even-steven, meaning your degrees are the same on the top and bottom, the way that we find this asymptote, in this case it'd be -1/4, but what you do is you take the ratio, so in this case even-steven, same degree, you take the ratio of coefficients. So the coefficient in front of -x² is -1. The coefficient in front of 4x³ is 4, so it's -1/4. And you're always looking at the highest degree for these. Okay. So to sum that up, bottom heavy rational functions, horizontal asymptote is y equals 0. Top heavy, there is none. And even-steven, the horizontal asymptote, is the ratio of coefficients. And it's always the top over the bottom. Okay. So what I'd like you to do here is just identify the horizontal asymptotes. So give it a try on your own. Okay, we're back. So this one we would call top heavy because your 6 is larger than your 1, so with top heavy we have none. For this we would call even-steven because we have the same degree, so we take the ratio of coefficients. So our asymptote would be y equals 2 because it's 2/1. And for the next, we have bottom heavy. 3 is greater than 2. So our asymptote is y equals 0. And if you'd like to continue, go ahead and graph those 3. You're more than welcome to. But the focus is just on the asymptotes. Okay. And that's it.